Hello everyone. In this video, we're going to go through some geometry problems, the sort of which that one could expect to find on the Canadian Math Kangaroo contest, specifically for grades 11 and 12. Before we dive into these problems, let's sharpen a few of the tools in our toolkit. So if we were to consider a circle, and we suppose that that circle has radius r. That means the distance from the center of the circle to its circumference, or perimeter. Then the area of that circle is given by squaring r and multiplying that by pi. Speaking of the perimeter or circumference of the circle, we can calculate that as it is equal to 2 times pi times r. Another important object in geometry is a right triangle. So that is a triangle where two of the sides meet at 90 degrees. And if we label those two sides that meet at 90 degrees, say we call one of them B and we call another one of them A, then the area of this triangle is given by A multiplied by B divided by 2. Now, this side that we've not labeled, this is called the hypotenuse, and if I were to mark it as C, then we have the famous Pythagorean theorem that tells us that a squared plus b squared must be equal to c squared.
Of course, also for right-angled triangles, we have the SOHCAHTOA rule. But perhaps a little less known is the equations for an arbitrary triangle. So it would have sides, say, A, B, and C, with opposite angles lowercase a, lowercase b, and lowercase c, where now these angles can take on any values, so long as it gives us a triangle. And in these cases, we have the sine rule, which says that sine of little a over big A is sine of little b over big B is sine of little c over little c. And we also have the law of cosines, which is like a generalized Pythagorean theorem, telling us that now c squared is a squared plus b squared, but we have to subtract off 2 multiplied by AB multiplied by the cosine of the angle across from C. There are many other important equations that are very useful throughout geometry, and the more of these you have in your toolkit, the more problems you'll be prepared to tackle.
In this first question, we're told that there are 3 circles tangent to each other, as you can see on the image on the right side of the screen. Each of these circles has radius r, and our task is to determine the area of the shaded region. So that is the region which lies inside the triangle and outside of each of the 3 circles. One way we could compute this is by first determining what the area of the entire triangle is, and then figuring out what the area of each of the portions of the circles within the triangle, and subtracting those portions off from the total area of the triangle. That should leave us with the area of the shaded region. Now, before I walk you through the solution of this problem, I highly suggest that you pause the video right now and give this question a good, honest try. See what you come up with, and then compare your results to the way that I've solved this problem afterwards. This is the absolute best way to make use of the content in this video, is to try it for yourself first. So before we compute this area explicitly, let's see if we can make an educated guess about what this might look like. We're going to be taking the area of some triangle, and we're going to be subtracting from it the area of some circles. We know from the previous slide that our formula for the area of a circle involves pi. So we should expect something to do with pi in this negative term over here. And at the same time, we probably shouldn't expect something to do with pi, which comes up in this triangle. So looking at all of our answers, which ones do we see a pi in the negative and only the negative term? Well, B has a pi in the positive term, E has a pi in the positive term, C has just one term with pi, and d also seems to have pi in both terms. So it seems from this initial estimate that it looks like the answer could be A. Of course, we should still check this to be sure, as it may turn out that the expression could simplify in some unforeseen ways, but it can be useful to look at a question and ask yourself intuitively first which answer you might expect. On the previous slide, we saw a formula for computing the area of a right-angled triangle, but this triangle doesn't look like it has any 90-degree angles to it. However, if we drop a line from the top point in this drawing, and I drop that line down in such a way that it's perpendicular to the bottom, I will then get two 90-degree triangles, and we can use our formula for the area of these to compute the area of the total triangle. So the question is then, what is the value of the height, h, of this new line I've drawn, and what is the value of the two bases of these triangles? Well, if I look at my drawing on the right, and I consider this top side here, notice that it's made out of two components. Now, since this line down the center cuts the base precisely in half, that means each of these two sides of the bottom have length r. Notice that the same reasoning can be applied to any of the other sides, so actually each of these sides has length 2 times r. But we still need to determine the length of h. Now that we have a right-angled triangle, we can apply the Pythagorean theorem. So this tells us that r squared plus h squared must be equal to 2 times r squared. Now, the exponent can distribute throughout the product, so this is just 4r squared. And so if I want to isolate h in this equation, I can subtract r squared from both sides and get that h squared must be equal to 3r squared. And that in turn will imply that h is equal to the square root of 3 multiplied by r squared. And since the root of the product is the product of the roots, this is just equal to the square root of 3 multiplied by r. Now, to get the area of one of these triangles, I can simply use the area formula, which tells us that r times h divided by 2 will be the area, is the square root of 3 multiplied by r. And so this expression is just given by the square root of 3 multiplied by r squared divided by 2. And since both of these triangles are just mirror images of each other, the area of the total triangle composed of both of these would just be 2 times this quantity. That is, the area of the triangle is given by 2 multiplied by root 3 multiplied by r squared divided by 2. So it is root 3 times r squared. Now we know that the total area of any one of these circles is given by pi r squared. However, we only want the portion of the area that is contained within this triangle. One way to do this is to figure out what the angle is that the corners of the triangle make within one of these circles. And then once we determine the proportion of this angle compared to the total 360 degrees that makes up a circle, then we will be able to determine the proportion of the area which is contained within this part of the triangle. Well, notice our triangle has 3 equal sides. They're all of length 2r. And so that makes this an equilateral triangle. That means that each of these angles are the same. Let's call that number theta. We also know that the sum of the angles of any triangle must add up to 180 degrees. So theta plus theta plus theta has to be equal to 180. In other words, 3 times theta must be equal to 180 degrees, and dividing both sides by 3, we get that theta must be 60 degrees. So the angle inside is equal to 60 degrees. So what proportion is 60 degrees of the total of 360? Well, to get that, we simply divide 60 by 360, which works out to 1/6. Therefore, the area inside any one of these given circles that is also contained within the triangle in the center has 1/6 of the area of the total circle. Therefore, the area of any one of these circles within the triangle is simply pi r squared, the total area, divided by 6. But since we have 3 of these circles, all of the same size, that means the total amount of area contained in the circles is going to be 3 times this quantity. And since 6 is divisible by 3, one of those factors of 3's is going to cancel out, and we're left with pi r squared divided by 2. Thus, as we pointed out earlier, the area is simply going to be given by subtracting the area of the 3 circles from the area of the triangle. So in other words, our final answer is 3r squared minus pi over 2r squared, and having a common factor of r squared, this factors out to give us root 3 minus pi over 2 multiplied by r squared. So we see that the final answer is A after all. Our intuition, our guess about what this answer should look like was correct.
For the second question, we're given this picture here of a square ABCD where all the sides have length 1. The arcs that we see are parts of the circles with centers given by the corners of the square, and we're asked to determine the length of PQ. Well, if I extend the line PQ so that it intersects the boundary of the square, and I take the new points on the edge to be y on the bottom, x on top, then I know the total length of x to y is equal to 1, since this has the same length as the sides of the square. And I can break this up into length from x to p, plus the length from p to the q, which is what we're trying to solve, and the length from q to y. So if I can figure out the lengths from x to p and q to y, we'll be done. Now the point P is on the circumference of the circle that is centered at C, and since B and D are both on that circumference as well, and they have length 1 from C, and we know that the circumference of the circle is the collection of all points the same distance from the center, the length from C to P must also be equal to 1. Furthermore, the line XY bisects the line CD, and therefore the distance from C to Y must be half of that. That is 1/2. So CYX gives us a right angle triangle, and using the Pythagorean theorem, we know that the hypotenuse squared, which is just 1, must be equal to 1/2 squared plus the length from P to Y squared. Rearranging these terms, we find that the length from P to Y squared is equal to 1 squared, which is 1, minus 1/2 squared is 1/4. So rewriting 1 as 4/4, we see this is 3/4, and taking square roots of both sides tells us that the length from P to Y is the square root of 3/4, or simplifying this, because 4 is a perfect square, root 3/2. So since we can also split up the line XY into x to P and P to Y, now that we know P to Y, we can rearrange these terms to determine that x to P is 1 minus root 3/2. Rewriting 1 as 2/2, we get that this is 2 minus root 3/2. Now, if we were to just repeat this situation upside down, that is, we look at the line from B to Q, since Q is on the circle centered at B, and we can use the exact same argument to determine that the length from Q to Y is also equal to 2 minus root 3/2. Plugging all of this into our red formula from the beginning is 1 minus 2 minus root 3 over 2 minus 2 minus root 3 over 2, which is 1 minus 2 times 2 minus root 3 over 2. But the 2 in the numerator and denominator cancel, and once we distribute this minus sign throughout, we're left with a final answer of root 3 minus 1. And thus the answer to our question is E. For the final question, we're given an equilateral triangle whose side lengths are 3 and a circle of radius 1, and they're overlapped so that their centers coincide. We're asked then to determine the perimeter of the shape. So first I'm going to draw these dotted lines, just highlighting where the actual sides of the triangle is. And I'm going to bisect each of the angles of this right angle triangle, which simultaneously bisects each of the sides. And I'm going to label this intersection of all the points O, which is the center of the equilateral triangle, and therefore is also the center of the circle. Now, the fact that there are pi's in these answers should suggest to us that the right thing to use in this problem is radians instead of degrees. So with that in mind, we notice that since this is an equilateral triangle, all the angles are the same, and they must add up to pi, which corresponds to 180 degrees. Therefore, each of the interior angles of the equilateral triangle have pi over 3 degrees, and thus the angle the side makes with the bisecting line, so bisection means cutting in half, has angle pi over 6. Now, from the symmetry, we can see that each of these sides are going to have the same length, so it's enough to determine the lengths for any one of these sides. And we see that the two straight portions must also have the same length, so it's enough to determine one of the straight portions. So we're going to label the two endpoints of that A and B, and we consider the triangle ABO. Since B is on the circle of radius 1 centered about O, we know that the length from O to B is 1. So by the law of cosines, the length of AB divided by the sine of its opposite angle, which we'll call beta, is equal to the side length of 1 divided by the sine of its opposite angle, being pi over 6. And pi over 6 is 1/2, so we have 1 over 1/2, which is equal to 2. So multiplying both sides by the sine of beta tells us that the length from A to B must be twice sine beta. So if we can determine beta, we should be fine. And we can do this if we can determine alpha. And again, using our sine rule, we know that sine alpha divided by its opposite side, which is the length of A to O, must be equal to sine of pi over 6 divided by the length of its opposite side. But sine of pi over 6 is 1/2 divided by 1 is still 1/2. So we multiply both sides by the length from A to O and take inverse sines to find that alpha is equal to the inverse sine of the length from A to O divided by 2. But we see that the length from A to O is also part of the right triangle involving AO and the point M where the bisector intersects. Again, bisector means it cuts it in half, so it must cut the length of the equilateral triangle in half. We're told each of the sides are 3, so the length is 3 over 2. And this is a right triangle, so now we can apply our rules of SOHCAHTOA, in particular the CA. So cos of pi over 6 is equal to adjacent divided by the hypotenuse, which is the length from A to O. So multiplying both sides by the length from A to O and dividing by cos of pi over 6, we get that the length from A to O is 3 over 2 divided by cos of pi over 6, which is 3 over 2 divided by root 3 over 2, which simplifies to 3 over root 3, which is just root 3. Therefore, alpha is just the inverse sine of root 3 over 2, but we have to be careful because inverse trigonometric functions always have two answers, namely sine of pi over 3 and sine of 2 pi over 3 both give us root 3 over 2. So how could there possibly be two different answers? Well, notice that there is one other point that has distance 1 from O. that is the other point of intersection of the circle with that side of the equilateral triangle. So comparing these two angles, we see that alpha must be the larger of these two, and therefore alpha is 2 pi over 3. So using that our angles must always sum up to pi, we know that pi is equal to alpha plus beta plus pi over 6 for the circle AOB, and that means that beta is equal to pi, which we can write as 6 pi over 6, minus alpha, which is 2 pi over 3, or we can write that as 4 pi over 6, minus pi over 6, which works out to pi over 6. Therefore, the length from A to B is twice sine pi over 6, and pi over 6 is 1/2, so 2 times 1/2 is 1. Therefore, the length from A to B is 1, as is the other straight segment along this side of the equilateral triangle. And we know that for a circle of radius 1, the whole reason why we use the definition of radians is because the arc length between 2 points is given by the angle that is made between the straight line from those endpoints to the center of the circle. Now we know that beta is the angle from the vertical to the nearest of these lines. And for the other possible solution we had with alpha, which corresponds to this larger red triangle, the leftmost angle is pi over 3. So the angle from the vertical to the furthest of these lines must be pi minus pi over 3 minus pi over 6, which is 3 pi over 6, or just pi over 2. And so the angle between the two red lines is just this larger angle, pi over 2, subtracted by the smaller angle, beta, and that works out to pi over 3. So that must be the arc length of this portion of the circle. Thus, the length of that side of the perimeter is 2 plus pi over 3, and since all three sides are identical, the total perimeter is just 3 times this quantity, which is 6 plus pi, and thus the answer is B. So that is all for this video. Thank you so much for watching. And if you have any questions, comments, concerns, the contact info is on the screen, so you can pause that, write it down, and find out more information either at mathkangaroo.ca or at info@mathkangaroocanada.com.